Alright, your homework was to take a look at page 188 through 189, and you had 3 elastic collisions and 3 inelastic collisions to consider. So we're going to go ahead and we're going to start with our elastic collisions with number 22. You had a ball of mass A, 0.440 kilograms, moving 3.3 meters per second to the right, and it collides with a ball of mass B, 0.220 kilograms, and it's initially at rest. We're going to determine if this collision is perfectly elastic, what their final velocities are. So we have an elastic collision and we have 2 sets of equations. We're going to be finding final velocity for A and B. We're going to be using the 2 concepts. With elastic collision, not only is momentum conserved, so we have initial momentum plus final momentum, or initial momentum of A and B equals final momentum of A and B. Since object B is initially at rest, we can reduce the equation down to the initial momentum of object A will be equal to the sum of the momenta of the 2 objects after the collision. Since it's a perfectly elastic collision, we also have conservation of kinetic energy, and we know that we can use the reduced equation that says that regardless of mass, the initial velocity of A minus B will equal the final velocity of B minus A. And we can reduce that down, since the initial velocity of object B is 0, to say that the velocity of object A initially will be equal to the velocity of object B minus velocity of object A. So we start with that equation, and we're using these 2 as a system of equations since we have 2 unknown variables, and we're going to solve for the final velocity of object B by rearranging the equation so that the velocity of A initially plus the velocity of A after will be equal to the velocity of B after. We plug that back into our conservation of momentum equation, and we distribute it here for object B. Distributing that in and placing in our mass variable 0.440 kilograms, 3.3 meters per second, and 0.22 kilograms, we would get the equation as such. When we rearrange that equation, we get that 1.452 is going to equal 0.440 VA prime plus 0.220 VA prime plus 0.726. We can rearrange that equation further, combine like variables, and we get 0.726 is equal to 0.660 VA prime. Solving for that, we get that VA prime is 1.10 meters per second. Now that we've got our first variable, we can plug it back to any original equation that we would like. The simplest equation is, of course, our velocity equation from conservation of kinetic energy. Plugging that in, we get 3.30 equals VB prime minus 1.10. Rearranging and solving, we get that VB prime is 4.40 meters per second. This is about the simplest form of an elastic collision problem that we could possibly get. Please take a note that all the way through, even though it wasn't specifically pointed out, we took consideration of the fact that momentum is a vector quantity and that this object had a direction, and since we established to the right, we called that the positive direction. Our solution, both values were positive, so that means that both objects are moving to the right after the collision also. Problem number 25 takes a look at a slightly more complex elastic collision situation where you have initially 2 objects, both of them moving to the right. So object of mass A and object of mass B both have initial velocity, so we have no 0 momenta quantities at the very beginning of the problem. And they have different masses. So the mass of object A and the mass of object B do not coincide. Again, it's a perfectly elastic collision. So since we've got a perfectly elastic collision, we're going to start with our 2 conserved quantities. Conservation of momentum, which is initial momentum of both objects is equal to the momentum after the collision for both objects, and conservation of kinetic energy, which is an equation that will work regardless of the object's masses. VA minus VB equals VB prime minus VA prime. Again, you're going to find that it's easiest to solve one equation for the unknown variable. I'll always be using the kinetic energy equation simplified for velocities. And here we've got some non-variable values. So when we plug in our initial velocity for VA and our initial velocity for VV, those are actual real number values, we get that VB prime is going to be equal to 1.35 meters per second plus VA prime. We can plug this into our conservation of momentum equation, and here we're going to have another distribution where here we have the initial momenta and the final momenta with our one variable plugged in. Plugging in our real values for mass and velocity for before the collision, mass and velocities for after the collision with our substitution. Combining like variables, we get 0.1 through 2 kilogram meters per second equals 0.15 VA prime. Solving for VA prime, we get that it's 0.88 meters per second. Notice that that's a positive value, so we know that VA prime, like the initial velocity, is moving to the right. And that does make sense intuitively, since we know that both objects originally were moving to the right. VB prime can then be solved by plugging VA prime back into the initial equation, and we get that VB prime is equal to 2.23 meters per second. Again, that's a positive value, so again we know that that object is moving to the right. So you can see that it's not much different. In fact, it's exactly the same problem-solving strategy, even though we had two objects moving initially instead of one object moving initially. The only other complication or quirk that could be added into an elastic collision like this for a straightforward problem-solving situation would be to have your momenta in opposite directions, and then you would need to establish one momenta as positive and one momentum as negative, and make sure that you track that throughout your equation. I've seen some of you make that mistake repeatedly, so please make sure in all of your problem solving that you are watching your vector quantities. This next problem I'm really kind of excited about, because it's very much like the type of problem that I hope that you get to the point that you're comfortable solving, since it's very much like the type of problem that you would see on some sort of an assessment. So here we're looking at a problem where you have one block of an arbitrary mass m getting slid down a 30 centimeter ramp to have a perfectly elastic collision with another object of different mass m, and then that object gets launched off of the ramp and falls 90 centimeters to the ground. And ultimately what we want to know is what the final velocity, what the final position of the little block mass m off of the ground after it's collided. And the only way to solve this type of a problem is to break it down into pieces. So the first thing to know is that this ramp that the large block mass m slides down is a frictionless ramp. So this frictionless incline means that if there's no friction, then there's no work getting done by non-conservative forces. So we're going to be dealing with conservation of mechanical energy for the transition of the block from, we'll call this energy position 1 to energy position 2, where it collides with the other block. The next thing to know is that you've got an elastic collision. So that means that down here at the bottom, you get that the sum of your momenta before is going to be equal to the sum of your momenta after. And if it's a perfectly elastic collision, we can also consider conservation of kinetic energy. And then third, our next topic that we're going to take a look at is once this object has its final velocity, it's going to leave the surface and then fall with projectile motion. And we know that for projectile motion, you've got a vector in the x and y direction, so that means that we're going to be solving for projectile motion for an object in 2 dimensions to ultimately solve for our very last piece of information, the distance away from the table that we're going to solve. So that means that we're going to be doing 3 steps of problem solving, each one getting a variable that will allow us to solve for the next variable. All right, so we'll take it from the first, conservation of mechanical energy, where because there's no work done by non-conservative forces, the mechanical energy at point 1 will be equal to the mechanical energy at point 2. At point 1, the mechanical energy of object M, so we're taking this block to be mass M, is going to be equal to mgh1, and we established that h1 is our 30 centimeter value up above the table. And at point 2, if we're down at the table at the point of collision, then that means that our mechanical energy at point 2 is going to be kinetic energy, or 1/2 mv squared. We can use this and we can figure out the momentum of the block before it strikes the other block. And we're going to do just that. We're going to say the large block mgh1 is equal to 1/2 mv squared. We can ignore the mass or get rid of the mass, and then we get that the velocity is going to be equal to the square root of 2gh1. We can substitute in our variables and say 2 times 9.8 times, and this is a 0.3 meter value. So we're going to go ahead and we're going to solve for that, and we get 2 times 9.8 times 0.3. We get that the velocity of the block before the collision equals 2.42 meters per second. So now that we know the velocity of the block at the moment before the collision, we can consider the fact that momentum is conserved. The initial block of small mass m is at rest. So that means that all of the momenta of the system is determined by the momenta of the initial block, large mass m, and that should be equal to, after the collision, the momenta of the large block plus the momentum of the small block after the collision. And if it's an elastic collision, then we know that the velocity before is going to be equal to VB minus VA. So let's go ahead and let's consider if this is in fact an elastic collision, which I'm going to do a quick double check, and we say elastically strikes another cube. So let's go ahead and let's look. Large m is going to be equal to twice the mass of the little mass block. So what we're going to do is we're going to do a combination there so that we can actually reduce our equation. So we get mv is going to equal mva prime plus 2, so 1/2 mv b prime. And now I can eliminate those masses, and I get v is equal to va prime plus 1/2 v b prime. And now I can solve. I'm very interested, exclusively interested in the velocity of VB. So we're going to solve for VB. And you get that V equals VA prime plus 1/2 V plus VA prime. Distribute, and I get that V equals 1/2 V plus VA prime plus 1/2 VA. And when I resolve that, I get that 1/2 V is going to be equal to 1.5 VA prime. I'm going to be distributing this through. I don't like having the 1/2 there, so what I end up getting is I get that V is equal to 3 VA prime. So that means that the initial velocity is 3 times the value of VA prime. So that means that VA is equal to 1/3 V for VA prime. And then solving for VB, VB equals V plus 1/3 v, and that means that VB is actually going to be equal to V prime is equal to 4/3 the initial velocity. 4/3 the initial velocity is going to be 3.23 meters per second. So, our initial velocity that we obtained from conservation of energy gave us the tool or the connection that we needed to use conservation of momentum for a perfectly elastic collision to determine the velocity with which the small block was launched off of the table. Since it's being launched off of the table, another important thing to remember is that that velocity, which is a vector, is directly off of the table. Since it's directly off of the table, we know that VB prime is only in the x direction. So that means that for our projectile motion equations, Vx equals VB. And Vy is going to equal 0. So that means that our y equation is going to be equal to 1/2 gt squared, since our Vy is equal to 0. So we can use that to solve for time. Time is going to equal 2y divided by g, and it's going to be the root of that, since 2 times 0.9 meters divided by 9.8, our time is going to be 0.43 seconds, which we then plug into our x equation. X will equal our VB velocity, 3.23 meters per second, times the time, 0.43 seconds. You can carry a third significant figure there if you'd like. And what I'm going to do is I'm going to multiply that by 3.23, and I end up with getting 1.38 meters, or approximately 1.4 meters. I carried 3 significant figures all the way through, but since my initial values are given with 2 significant figures, my final answer is rounded to 2 significant figures. So this is a really great example of how to use multiple concepts together. It's a 3-step problem where we're taking a look at how we can use the conservation of energy, conservation of momentum, and some kinematics to figure out an ultimate answer to a question that's built around multiple steps. So let's go ahead and let's jump forward into inelastic collisions. The major difference between elastic and inelastic collisions is that in an inelastic collision, conservation of kinetic energy does not apply, whereas conservation of total energy does apply. So number 33 asks us to derive a formula for the fraction of kinetic energy lost for the ballistic palindrome collision of example 7-10, and we're going to evaluate for the small mass 14 grams and the large mass of 380 grams, but we're going to hold off on plugging these in, and we're going to solve with variables. So we're going to go ahead and we're going to take a look first with deriving the formula. And in example 7-10, you've got a little bullet, and that little bullet has a kinetic energy that's equal to 1/2 the little bullet's mass times its velocity squared. And since that little bullet collides with the ballistic pendulum, then you know that the kinetic energy afterward that exists is going to be equal to 1/2 the sum of the masses times velocity squared. And that's going to be a final velocity. And you don't know the relationship of those two just yet. You only know that the initial velocity and the final velocity are going to be related by the equation v prime equals the little mass m plus m v. And we got that using our conservation equations, so that we were able to determine what the ratio of initial and final mass is. So now we've got this substitution value that we can use, and we're going to do just that. We're going to plug it into the ratio, the change in kinetic energy divided by the initial kinetic energy. And remember that the change in kinetic energy is just the final minus the initial, and the initial is just kinetic energy at point I. I'm going to try and be consistent with my symbols. So now I'm going to do just a little bit of factoring here. I get 1/2 m plus m v prime squared minus 1/2 m v squared divided by 1/2 m v squared. Now, there's a 1/2 in every single one of those variables, so we're just going to reduce a little bit, and we get that m plus m, and m over m plus m times v, and then we're going to square that, minus mv squared all over mv squared. So we've substituted in for our v prime here. All right, this is this. Next, we're going to reduce and combine like variables. So moving through, we've got m squared v squared over m plus capital M minus mv squared over mv squared, and we're going to notice you have mv squared up here, mv squared there, so we're going to reduce, and you end up getting m minus 1 over m plus m, and that can be rewritten algebraically as negative m over m plus m. Now, we have our equation for the loss, or the ratio of change in kinetic energy to the initial kinetic energy, and so now all we have to do is we have to plug in our masses. So for our given masses, we can plug in negative 380 grams divided by m plus m is going to be 380 plus 14, or 394 grams, which gives us the ratio of negative 0.96. So that means 96% of all kinetic energy is lost during that collision. And remember, it's lost to other forms of kinetic energy. So that gives you a really great idea of what we can do. We can look at how kinetic energy changes and what ratio of kinetic energy we're actually losing when we're doing a problem like this. Alright, now we're going to take a look at an explosion, which is another type of inelastic collision. Here again, it's an inelastic collision. The kinetic energy is not being conserved, but the total energy is conserved. And the momentum is also conserved also. So in an explosion, you definitely have to pay attention to your vector quantities. So in an initial explosion, an object breaks apart into two different pieces. One has 1.5 times the mass of the other. And we know that 7,500 joules were released in the explosion, so we're going to determine the kinetic energy that each piece acquired. So we know that the kinetic energy before is equal to 0, and the kinetic energy after is going to be equal to 7,500 joules. And we know the ratio that one mass is actually 1.5 times the value of the other mass. So conservation of momentum, initially the object is at rest, and then there is a collision, so that means that the sum of the momenta after the collision is going to be equal to still that 0 value. So let's go ahead and let's take a look. The initial velocity, so we have MAVA prime plus MBVB prime, and we're going to rearrange that so that the velocity VA prime is equal to negative MBVB prime over MA. And since we know the ratio of 1 to 1.5, that means that that ratio is going to end up being negative 2/3 VB prime. The negative sign here that we got from rearranging the equation is actually going to be indicating the direction. That means that VA is opposite the direction of VB. And to establish, MA is going to be equal to 1.5 times the mass of MB, and that's what happened when we plugged them in right here to reduce to this fraction. So, since there's no mechanical energy before the explosion, the kinetic energy of the particles after the explosion must equal the energy added. So the energy added, because the kinetic energy is not conserved, is going to be equal to Ka prime plus Kb prime, and that's going to be equal to 1/2 MAVA prime squared plus 1/2 MBVB prime squared. And now we're going to plug in our m's, and you get that it's equal to 1/2 1.5 m 2/3 VB prime squared plus 1/2 MBVB prime squared. And you notice I dropped out that negative value because that value is going to get squared. So we reduce and combine like terms in the equation, and you end up with 5/3 times 1/2 MBVB prime squared will equal 5/3 Kb prime. So Kb prime equals 3/5 the energy added, and 3/5 times 7,500 joules is going to be equal to 4,500 joules. So that means that the remainder is going to be kinetic energy of A. So if Kb is equal to 4,500, then that means that Ka by definition would be 7,500 joules minus 4,500 joules, or 3,000 joules. So Ka equals 3.0 times 10 to the third joules. Kb prime is equal to 4.5 times 10 to the third joules. So that's another way of looking at the changes in the ratios of changes of kinetic energy when we can't determine what amount is conserved. Last but not least, I love this problem so much, and you're going to be doing a lab in just a moment related to this problem. We're going to be determining the coefficient of restitution given by the symbol E. And that coefficient of restitution is the measure of inelasticity of a head-on collision between two objects. So, the coefficient of restitution is given by this variable E, and it's VA prime minus VB prime over VB minus VA. And in this equation, what we're looking at is we're looking that VA prime minus VB prime is the relative velocities after a collision for two objects. And remember, that's going to be from your frame of reference. And then VB minus VA is the relative velocities before the collision. So the first thing we're going to look at is, if this is our equation for coefficient of restitution, we're going to be looking at two situations. We're going to show that for a perfectly elastic collision, the coefficient of restitution would equal 1. And that for a perfectly inelastic collision, and this is going to be elastic, and for a perfectly inelastic collision, the coefficient of restitution is going to be 0. So let's go ahead and let's dive right in to show these two proofs before we look at what we're going to be doing today in the classroom. For a perfectly elastic collision, we know that VA minus VB is equal to negative VA prime minus VB prime. So that means that the simplest form of showing this is you get that if I rearrange this equation, then what I could likewise show is I could show that negative VA minus VB is equal to VB minus VA. So what I can do then is I can plug it in and I can say that VB minus VA is equal to the same thing as saying that VA minus VB. When you do that, you get that VA prime minus VB prime over VB minus VA can be substituted in there. Then it's VA prime minus VB prime over VA prime minus VB prime, which gives you the ratio of 1. So that's going to be your solution for an elastic collision. For a completely inelastic collision, we know that after a collision, VA prime is going to be the same as VB prime because the two objects are stuck together. So if we substitute that into a collision, then what we're going to see is we're going to see that E equals VA prime minus VB prime divided by VB minus VA. Well, if these are the exact same value, then it's going to be V minus V would equal 0 on the top. It doesn't matter what's on the bottom. That's 0 for a perfectly inelastic equation. The next thing that we're going to look at is exactly what you're going to be doing in the class today. Here we have a situation where you have an object, a ball that's going to bounce, and what we're going to do with this ball that's going to bounce is we're going to be measuring the coefficient of restitution for the ball colliding with a hard surface. Your hard surface, this is a steel plate in the book, your hard surface is going to be either, your determination, the floor or the countertop or the desktops. So what we're going to do is we're going to measure the height that the ball bounces back, h prime, based on the height that the ball bounced initially. And how we're going to do that is we're basically going to derive a formula for the coefficient of restitution in terms of heights instead of velocities. So that means that you're not going to be using any kinematic tools to measure velocities. All you're going to do is you're going to determine the coefficient of restitution of the ball using only the initial and the final height after the collision. So here's how we're going to do it. We're going to say that object A is the ball, and we're going to say the object B is the plate. So the speed of the steel plate before the collision is equal to 0. And here's a fun thing, the speed of the steel plate after the collision is still 0. If you don't believe me intuitively, then go ahead and bounce your ball on something and see how much the countertop or the table doesn't move. So now that we've determined that the steel plate velocity before and after are going to be equal to 0, then we know that the coefficient of restitution is going to be VA prime minus 0 over 0 minus VA. So that means our coefficient of restitution here is going to be negative VA prime over VA. So here we've got our coefficient of restitution equation. And now we're going to have to think about how we're going to solve it. So energy conservation for this situation, when we're in free fall, if we can neglect air resistance, which we can here, we know that E1 is going to equal E2 for the initial. So E1 is given by mgh, our initial height. E2 is going to be given by 1/2 mv squared, where v squared is actually VA squared. So that means that mgh is going to be equal to 1/2 mva squared for before the collision. So now I've got a way to solve for this value down here for VA. Likewise, what's happening here? Well, when the ball initially bounces off and has velocity, that velocity would give the kinetic energy of 1/2 mv prime squared for the velocity. And since we're still neglecting air resistance, that should give the value mgh prime after the collision. So mgh prime equals 1/2 mva prime squared. So now I'm going to solve for VA and VA prime. And I get my mass is negligible, thank goodness, not going to have to put a ball on a balance. And I get that VA is going to be equal to the square root of 2gh. And I get that VA prime is going to be equal to the square root of 2gh prime. So now I get the coefficient of restitution is equal to negative the square root of 2gh prime over square root of 2gh. I can reduce, and I get that my coefficient of restitution is going to equal the square root of h prime over h. So now that you've done this derivation for your homework problem, what you're going to do is you're going to determine the coefficient of restitution for one happy ball and one sad ball using multiple trials. Go ahead and grab them out. They're up at the front of the classroom. I want this derivation in your notebook along with a background that explains what the coefficient of restitution is showing, and I also want you to explain how you're using the concept of conservation of energy and how you're showing a change in energy during this collision.